Alrighty, we're going to talk about dependent probabilities, and our definition for dependent is relies on others. So that might be other things, other people, and in the case of probability, it is talking about other events, okay? It's talking about the event that came beforehand impacts the probability of whatever event comes next. So what that means is that the first stage of whatever our experiment is, or whatever we are finding the probability of, is going to change the probabilities for the next stage, for the second stage, and so on and so forth. So whatever happens before has an impact. Okay. Our key phrase with this is without replacement. What that means is that whatever we're doing, we are not putting back whatever marble we pulled from the bag, or whatever card we drew from the deck, or whatever person we selected to fill a role. Okay, we're not putting it back. It is not being replaced. That is what's going to change our probabilities. So we're going to do a little example together using a bowl of starbursts. Okay, now if I want to know what are my options for picking out 2 starbursts from the bowl, well, I'm going to start by looking at what do I have to start for the first starburst that I pull. Because even if you pull out 2 at the same time, really what you're doing is you're pulling out one and pulling out another right after it, okay? So probability-wise, we can break it down into that. So I want to know pulling out 2 starbursts. Okay. Well, first of all, I have 3 different kinds of starbursts to start. So my first starburst could either be red, could be pink, or it could be yellow. And I'm going to include what their probabilities are. Well, let's first count how many red there are. There's 1, 2 red out of a total of 1, 2, 3, 4, 5, 6, 7 total candies. Pink, there are 1, 2, 3, so I have 3 out of 7. And yellow is also 2 out of 7. So that indicates the first stage. Now I'm going to actually do an example of that. I'm going to pull out this red candy. And what that means is that I am now sitting at this spot on my tree. If I started here, my first stage I got a red, so I follow that branch. So for the second pull, I'm going to draw that off of this option. Okay? Well, now I still have red, pink, and yellow as my options. Red, pink, and yellow. But now my red, I only have 1, and my total is 1, 2, 3, 4, 5, 6. Pink, I still have 3, but my total is 6, and yellow, I still have 2, but my total is 6. So this is my second draw. If my second draw is a red, this is what that tree would look like. But I don't know if it's going to be a red. So I'm going to put that red one back. I've now reset. So I'm like in the first stage again. And this time I'm going to follow my pink path. So I'm going to put a pink here to represent that we are on the pink path. When I pull out that pink one, I still have 3 options for what that second starburst could be. It could be red, it could be pink, it could be yellow. My probabilities are now 2 out of 6, 2 out of 6, 2 out of 6. So that is the possibilities for if the first pull is a pink one, what could the second one be? So we've taken care of what could it be if I pull down a red, if I pull down a pink. Now I'm going to pull out a yellow in my first draw. And we're going to draw ourselves the tree for that. So again, I have 3 options for that second one. It could be red, it could be pink, it could be yellow. My probabilities are out of 6. This should be 2. 1 out of 6. So now I can look at what are some potential outcomes. I'm not going to write the whole sample space, but if I wanted to know the probability of choosing pink and then yellow, I would follow the pink path, pink, and then my yellow path off of pink. So I get that is equal to 3/7, because that's the number on my pink path, times 2/6, which is the number of yellow off of the pink path, or 6/42. So this is an example of a dependent situation because I did not put my pink candy back the first time that I pulled it out. I pull it out of there. I didn't put it back. And so the total number in the bowl has now changed, which impacts all the other probabilities, regardless of what the first draw is. Okay. We're going to do another example, this time with some Jolly Ranchers. And my thing is I want to pull out, have 3 people get a Jolly Rancher. Okay, well, 3 people are going to get a Jolly Rancher, which means that one person's going to draw a Jolly Rancher out, then another person, then another person. So I'm going to have 3 different stages to my tree. Okay, my first stage, or my first person, has 2 options. They can either pull out a blue or a purple. B for blue, P for purple. Well, what's my probability of blue? 4 out of 7. What's my probability of purple? 3 out of 7. Okay, well, if I pull out this blue one here, then for the second person, they can either get a blue or a purple, but their probability is going to be 3 out of 6, 3 out of 6. Okay, if the third if that second person pulls out a purple, well, then my options are still blue and purple, but my probability is 4 out of 6 and 2 out of 6. So that's what could happen for that second person. We always look at the second person or the second thing after I've pulled out one thing. So we start we take the probability before the action happens. So I'm going to reset us to the start situation. So right now we're here. I'm going to pull out a blue one, so meaning that I'm following the blue path. And so now I'm looking at the probability for the second person. For the third person, I'm going to pull out this second Jolly Rancher, a blue, which means I'm on the blue path, and I have 2 options. I can get a blue or a purple for my third person. Probability of blue is 2 out of 5. Probability of purple is 3 out of 5. I'm going to put back that last piece so I can look at what would the probability be if it went blue and then purple. Well, if it goes blue and then purple, I still have 2 options, blue and purple. And it is a 3 out of 5 and a 2 out of 5 probability. Okay, I'm going to go back. And this time I'm going to say that I pulled out a purple. And then I pulled out a blue. My possibilities are blue and purple. So I'm following the path and then writing what is left over for that third person. And they have a 3 out of 5, 2 out of 5 chance. Okay. Then I'm going to put my blue one back so I can follow my purple train. They've got blue and purple. We've got a 4 out of 5 and a 1 out of 5 chance. Now the probability that I get a blue and then a purple and then a blue, I'm going to represent on my tree. So I'm going to follow the path that shows a blue first, and then a purple, and then a blue. And so those are the numbers I'm going to use, those numbers on those paths. So 4/7 times 3/6 times 3/5, which is equal to 36 over, I believe, 210. As a decimal, or a percent, I mean, we're going to do a percent to give a little more meaning to our numbers here. 36 divided by 210 is 17% chance. So there's a 17% chance of this outcome happening. Okay. So that's how we have a dependent. We have the probabilities changing. The key thing is that our denominator switches, or our denominator changes. So if you take away anything, your denominator, or bottom of your fraction, will decrease with each stage. Okay. Another important thing we learn here is the importance of keeping our stages straight, or organized, so that we can see very clearly the probability for the first person, second person, and third person.